Okay, so now we're going to move on here, still discussing resonance. But in this particular lecture, what we're going to focus on is being able to spot molecules that have resonance associated with them. Okay, so these can be lumped into 5 categories, and we'll go over sort of what these are more in depthly here following this, but just sort of denote here. You're going to see this word allylic a lot, so that's going to be one of the things that we're going to define in this lecture. And so these are these types of categories here. So if you have a lone pair located in an allylic position, and again, we'll go over what that is in a second, that will have resonance, or if there's a charge in the allylic position. Another one that's might be a little bit more easy to understand with the terminology that we have now is if you have a lone pair adjacent to a positive charge. Anytime you have a heteroatom with a lone pair right next to a positive charge, you know that there's going to be resonance associated with it. A pi bond between 2 atoms of differing electronegativity. So any polar pi bond, that will have resonance. And if you have conjugated pi bonds, which are pi bonds that are located right next to each other with a one right after the other with 1 sigma bond in between, as is sort of written here, right? So these are all pi bonds. There's just 1 sigma bond separating them. Compounds like this will also have resonance associated with them. So now let's dive into each of these categories here. So first of all, this vocabulary. This idea of allylic as well as vinyl, 2 closely related words, always are associated with double bonds. Okay, so they're positions of a double bond, or rather positions within a compound that contains a double bond. So the vinyl atoms or the vinylic positions are those sp2 carbons that are participating in that double bond, right? Both of these guys here are sp2 hybridized. They've both got p orbitals that are pi bonding together through side-to-side overlap. Those are your vinyl positions, your vinyl carbons. The allylic positions, which are the ones that actually turn out to be even more interesting in terms of resonance, the allylic positions are those located right next door, right? So your allylic position is what's bound to the vinyl carbon, all right, or located 1 away from that double bond. So now let's talk about really what we're going to be interested in is identifying allylic lone pairs versus vinyl lone pairs. Or really just allylic lone pairs. That's what we want to be able to spot. So this is when the lone pair is located on an atom that's bound to that vinyl carbon. Okay, so this nitrogen is in this allylic position. Its lone pairs in this allylic position. This is a way to spot a structure or a molecule that has resonance, right? If you find a pair of electrons, a lone pair located in the allylic position. Notice that this nitrogen is not. It will not have resonance associated with it. It's just too far away. In particular, this guy here is what messes this up, right? Because this is sp3 hybridized, and so there's no p orbital that's available for these electrons to move through to that double bond, right? You got to have those p orbitals all in a line. That's a key to resonance. So if we want to locate pairs of electrons that are in allylic positions, these are just sort of an illustration of all those different possibilities. You could have a carbanion that's located in allylic position. That's going to be resonance stabilized. A pair of electrons on an oxygen, including if you remember what this functional group is called, this is an ester. This carbanion is going to be in an allylic position. Notice that the pair of electrons on this nitrogen are not. They are not going to be involved in resonance. And then lastly, again, we should know what this functional group is. This is an amide or an amide. And yes, those also have resonance associated with them. So now let's draw our arrows to show exactly how these electrons move in this resonance, right? So we're going to do the base of our base of our arrow is going to be at this pair of electrons. That represents the formation of a new bond with that carbon. And this pair of electrons, carbon can't have 5 bonds there in the middle, so at the same time, that pair of electrons has to jump to that terminal carbon. And so what we get is the sort of exact reverse of what we had above, which is that carbanion has moved. And again, what's being represented here is the stabilization of that negative charge as it's being dispersed around that molecule as opposed to isolated on a single atom. So again, in all these resonance structures with regard to the allylic lone pair, you're always going to start with that base of your arrow at the pair of electrons, form that new bond. That's going to kick that up. Now this first move also formed this bond here, and that means that my oxygen has to have a formal charge of +1, right? I'll draw in the lone pairs. Again, we really don't draw the lone pairs because this is something that everybody's so new to. I'll be pretty explicit, but at some point you can expect for those to sort of disappear. Yeah, I mean, it's the same pattern all the way down. How about you guys give it a shot for the amide? All right, so see if you can't tell me what the other resonance contributor would be for this structure. All right, so just like before, we're going to have this pair of electrons come down, this pair come up. Okay, so if you didn't get this far, this is what the arrow pushing does to my electrons in terms of bonds that are formed. Now go in and make sure that to fill in all formal charges. All right, so since this pair of electrons jumped up onto that oxygen, that means that my oxygen has a negative formal charge, which makes sense because oxygens with 1 bond must have 3 lone pairs, and thus a negative charge. And likewise down here, this nitrogen has 4 bonds, so that should be a formal charge of +1. Okay, so first thing to spot, that you first class of molecules that you can spot and know have resonance is when you have an allylic lone pair of electrons. That allylic lone pair will jump into that P network of orbitals, right? So that's going to be what's dispersed through resonance. Another pattern is also dealing with the allylic position, but this is allylic positive charges, really any allylic charge, although we did deal with negative charges over here. So allylic positive charges are also resonance stabilized. If we want to see what that looks like, similar to before, the difference here though is that it's actually going to be those pi electrons that are moving into the empty p orbital on the carbocation. Right, so in this case, this is the jump that you would see, right? Different from the previous slide where the base of our arrow was a lone pair. Now the base of our arrow is the pi bond. And this can happen, you know, if you have a large network of what are called conjugated pi bonds, or again, they're 1 apart, this can happen in multiple jumps. So for example, here would be 1. That would get me the following. And now my positive charge is located here. Notice that this is also an allylic positive charge. So this pair of electrons can jump there. And what that did was disperse that positive charge over an even larger network of pi bonds, stabilizing it that much more, right? So the more resonance contributors you can draw, the more stable that molecule is going to be. All right, what happens when you have a lone pair adjacent to a positive charge? Okay, so 2 examples here. One of them is just the reverse of what we saw on our first slide. But now we have this pair of electrons coming down to fulfill that positive charge, giving us our neutral molecule, right? Conservation of charges, -1 + 1 should equal 0, and I got 0 over here, right? This is just a lone pair of electrons that's going to be moving into an empty p orbital on a positively charged species. Another example that would that doesn't lead to a formal charge of 0 is if you have, what do we call this functional group here? An ether that's located right next to a carbocation. So an ether can stabilize a carbocation at the very adjacent positions because it can lend a lone pair of electrons down, and then that positive charge is now distributed onto that oxygen atom as well. Okay, so this is what happens when you have a lone pair adjacent to a positive charge. You can also draw resonance structures whenever you come across that situation. So now what happens when you have a pi bond between atoms of different electronegativity? The pair of electrons can jump onto the more electronegative atom. So in this case, the oxygen can only allowed to happen when you have a carbon there, right? Because you're inevitably, well, if you're going to remove somebody's octet, right? Remove electrons from somebody's octet, it has to be carbon. It can't be nitrogen or oxygen. So this is something that a resonance structure that you commonly seen associated with, what kind of bonds are those? With carbonyl bonds. Carbonyl bonds have resonance that will leave a positive charge on the carbon at that base, that carbonyl carbon. This is one that we haven't talked about yet. It's actually called an imine. Don't worry about that until next semester maybe. But nonetheless, it has the same sort of situation. You have a pi bond that exists between atoms of different electronegativity. And so what we have is similar. Okay. So another instance that you're going to spot resonance in, again, primarily going to be this when you see a carbonyl bond. And then the last one is sort of one that maybe you would have talked about before in talking about aromaticity, but this is what happens when you have a conjugated network of pi bonds, or pi bonds that are located next to each other, separated by just one sigma bond. Okay, and that's true whether they're in a ring, that's great, or even if they're in a long line like so. This is also an example of conjugated pi bonds. When they're in a ring, your resonance structures are all neutral, so that's why that's like extra special. If we draw the resonance structures for this, draw all of them. You would see that actually what we create through resonance, this bond jumps there, this bond there, and now this pair of electrons is here. Of course, conservation of charge, right? Forgot over here, since I took that pair of electrons away from that terminal carbon, I'm left with a positive charge on there. Okay, but conjugated networks of pi bonds are also going to be patterns to spot for resonance. And again, that by conjugated, it means that you have pi bonds that are separated by a single sigma bond. Okay, and again, the important feature here is these p orbitals that are located right next to one another, right? So this is a breakdown of this molecule. This is actually a pretty famous organic chemistry molecule. This is benzene. We'll see. We actually won't spend a ton of time on this until second semester, but we'll see it around. Benzene consists of a bunch of sigma bonds, right? Sigma bonds between the carbons as well as between carbon and hydrogen. But most importantly, it also has these p orbitals that are lined up all one next to one another, as is pictured here, right? So these are all p orbitals, and there are pi bonds located in every other orbital, or pi bonds located in every other slot. But of course, these are all in resonance with one another. They're all conjugated. So the real way to think about this, these orbitals are as if they're melded together, forming this delocalized pi system across that ring. All right, so everybody, I want you to take these examples. This is one set from each category and see if you can't pick out which of these compounds are actually exhibiting resonance. So pause the video, give it a shot, and then you can play it back and check your work. Okay. For A, it is this compound here that exhibits resonance, and that's because we have a lone pair located in an allylic position. Remember, allylic lone pairs exhibit resonance. That's what you see here. This pair of electrons can come down, and this pair jumps up here. All right, so the allylic position was one of those ones you want to be able to spot. Likewise, allylic positive charges was another example. So in this case, it's this middle one. And the resonance that's available here is this pair of electrons moving that double bond over there. Okay. Which of these exhibit resonance? In this case, we have our lone pair located adjacent to a positive charge, right? That was another pattern to spot. So if I were to draw in that structure, it would be this lone pair coming up here. Notice that oxygen does not break its octet, but it does now gain a formal charge of +1. Okay. It's actually both of these two here, because these are pi bonds that are located between atoms with differing electronegativity. So both of these would have resonance structures associated with it, where this pair of electrons gets stolen from that base carbon onto the more electronegative heteroatom. All right, and the last ones are both the benzene ring, of course, but also this guy over here will exhibit resonance. It's got 2 pi bonds that are located with just a sigma bond between them. All right, so that is also going to have resonance associated with it. If I were to draw the resonance structures for these, be something like this. It's a good idea to practice what the resulting structures of all these are, right? One of the things that we should have learned from Resonance 1 was how to follow our arrows. So make sure to double check and that you can do that with these examples here.